After studying this module, you shall be able to know about the drawbacks of macroscopic kinetics, study the molecular reaction dynamics, know about the molecular beam experiment and study of potential energy surfaces. Introduction. The average behavior of an association of molecules of the reacting system are governed by statistical treatment of the collision theory and activated complex theory. This is called macroscopic kinetics. Only indirect fact about the specific molecular events are transferred, and also there is a range of energy states of reactant molecules during a chemical reaction. This leads to a drawback of molecular kinetics. D.R. Hirschbach, Y.T. Lee and J.C. Polanyi did the great work by introducing the new branch of molecular reaction dynamics or microscopic kinetics, and also won Nobel Prize in Chemistry in 1986 for this. Reaction dynamics deals with intramolecular and intermolecular motion which takes place in elementary act of chemical change and with quantum states of reactants and product molecules. But macroscopic kinetics cannot be replaced by molecular reaction dynamics, as the latter only tends to achieve only elaborative picture of elementary chemical act and molecular beam process as experimental technique examined by using a monoenergetic beam of atoms or molecules. The narrow beams of atoms or molecules are allowed to cross each other, and their directions and speed of products and unreacted species can be evaluated. This process is called molecular beam investigation of a bimolecular reaction. The distribution of energy and angular momentum amongst the reactant molecules, the quantum states of product molecules, the dependency of total kinetics on the states of reactant molecule can also be studied by this analysis. Figure shows the systematic apparatus used in molecular beam experiment. The two main distinct features of the apparatus are the tremendously thin beam of reactant are generated with necessity for regulating the speeds of molecules and their rotational, vibration and electronic states by the devices. The reaction products are identified by movable device at several locations. In the molecular beam experiments launched in 1930s, the beams were generated by considering the reactants in a small vessel with a very minor opening permitting the atoms or molecules to effuse into an empty vessel. A regular slit is used as the orifice, and second small slit besides it allowed the molecules transfer in the essential direction. The beams generated had a very low intensity, and spread of molecular velocities had affected these early molecular beam experiments. Supersonic nozzle sources have overcome the drawbacks and can generate beam intensities larger by about 3 orders of magnitude. Figure shows the schematic diagram of a typical nozzle beam source. The gas which is used is taken in an oven at a pressure several folds of magnitude larger than that used for effusive flow. The molecules evolving via slit form a slightly divergent beam at supersonic velocities. A part of a beam is allowed to travel through a specially designed skimmer which picks only the core of the beam. The beam eventually arrives the main scattering chamber via slit by passing via some empty vessels. Therefore, the generated molecular beams have a very thin range of molecular speeds and greater power than effusive beams. By changing the oven temperature, the translation kinetic energy of molecules can be changed. A technique seen is used for raising the energy range of heavy molecules with a large amount gases that appears from oven at high velocity and sweeps the heavier molecules along with it. The heavier molecules travel along the center of the beam while the lighter molecules are dispersed towards the edges of the beam and are studied using suitable techniques. Therefore, due to the collision of molecules in the crossed molecular beams, the following processes might take place. First, elastic scattering, when there is a zero energy transfer among various degrees of freedom. Inelastic scattering, where the energy is transferred among different degrees of freedom, but the chemical reaction takes place, is called inelastic scattering. Third, reactive scattering. When there is a chemical change, it is called reactive scattering. This is of utmost importance. Differential surface ionization detectors was used in early examinations, which was based on the principle that the alkali metal atoms and their salts get easily ionized when they came in contact with a heated wire or appropriate work function. This technique was restricted to the reactions of alkali metals only. Mass spectrometers are used in latest work in the analysis of scattered beams. A time of flight in mass spectrometer has been used for studying the velocities of the scattered beam in all types of reaction. The chopper is kept in the front of mass spectrometer and is revolved at high speeds. The time required by product molecules once they passes through chopper and to reach the detector depends upon the translation velocities. Consequently, the distribution of speeds in the scattered beam can be found out. Potential energy surfaces. Suppose one of the simplest reaction, that is D plus H2 giving DH plus H. We would require three spatial coordinates to elaborate the configuration of this reacting system at any point along the reaction path. These coordinates are the internuclear distance R1 between H and H, the distance R2 of D2 from the midpoint of the HH bond, and the angle theta between HH bond and the vector from the midpoint of the bond to D. Although from D to HH bond is energetically more favorable than any other, but the path formed which D approaches HH bond along the line of center of the three body system, that is, the angle theta is either 0 to 180 degree. It is because when D approaches HH bond along theta is equals to 0 degree, it experiences considerable repulsion from any one of H atom, but while in case of any other angle, D is repelled by both the H atoms. When D atom is closer to HH bond, along the line of center of atoms, the potential energy is governed by the distance DH and HH. If one distance is plotted along x-axis and other along y-axis in a plane, the potential energy can be plotted along z-axis. Thus, the potential energy V of the reacting system can be drawn as a surface in three dimensions. Although the computational techniques were not to update in old times, so researchers were not able to perform a purely theoretical calculation and had to depend on semi-empirical approach based on spectroscopic data. In 1915, R. Marcellin suggested the idea of indicating a chemical reaction by potential energy surface only. In 1931, H. Eyring and M. Polanyi actually computed the first potential energy surface. More accurate calculations were performed later by them by combination of calculations and intuition which was correct. Figure shows the surface in the form of three-dimensional model. The reaction path over the surface can be easily traced. There is a path from the reactant to the product side that follows the counter of minimal potential energy. If the interconversion of translation and vibrational energy is assumed, then the reaction path appears like that of a bobsled sliding on its run. The path crosses a deep valley, increases over a hump to a saddle point at the activated complex, and then crosses down into the other side of another valley. This reaction path is called the reaction coordinate. This raise in the saddle point is of 38 kilojoules, which is equal to the activation energy of the reaction. This depends on the configuration of the activated complex, where R1 is equals to R2 is equals to 93 picometers. This distance is significantly larger than the normal interatomic distance, that is 174 picometer in H2 molecule. The plot of a chemical reaction from beginning to end is provided by the potential energy surface. For any reaction, there is always a specific configuration at saddle point. The activated complex is like a normal molecule except that it is not an equilibrium configuration. So, we can consider a reaction to take place in two stages, that is, the formation of the activated complex from the reactants and the decomposition of the activated complex into products. These are not well defined stages, and from a dynamic point of view, the reaction occurs smoothly and continuously. We can say that a transition state is the highest region of potential energy surface along the reaction path. Kinetic theory provides us important information about molecular collisions, but it does not tell changes that occur at the molecular level when the reactants are converted into products. When there are two molecules close to each other, they cannot be assumed separate because of overlapping of their wave functions. Therefore, from the time the reactant molecules are close to each other till the products are separated, the system is a sort of supramolecule. Although this supramolecule is different from normal molecules as it is changing, but the molecule can be examined by its energy and the electron distribution for each nuclear configuration by applying quantum mechanics. The movement of electrons and wave functions can be found out by applying Schrödinger wave equation, as Born-Oppenheimer approximation says that the movement of electron is much faster than that of nuclei. Schrödinger wave equation might produce the more vibrational energy levels, so this technique was used to identify the electronic potential energy function. For the reaction involving n nuclei, there are 3n nuclear coordinates, 3 translation coordinates of the center of mass, and 2 or 3 rotational coordinates about the center of mass that do not affect the potential energy. So, when the nuclei are constrained to a straight line potential energy, a function of 3n minus 5 coordinate is applied, and when the nuclei are not on a straight line, 3n minus 6 coordinates in general. For the simplest type of reaction of A plus BC giving AB plus C, where A, B and C are atoms, so the 3 coordinates are needed, but the plot of potential energy as a function of 3 coordinate is impossible only if the angle theta come close to A to BC is fixed. The potential energy can be plotted as a function of RAB and RBC, where R is the intermolecular distance. As RAB is seen large on the left face of the diagram, the potential energy is basically that of BC molecule. Likewise, the right face gives the potential energy of the AB molecule. The RAB distance is very large. As A come close to BC, the lowest energy path is provided by the dashed line from reactants R to products P. The minimum energy path, also mentioned as reaction coordinate, is seen by dashed lines. The system does not actually move along the reaction coordinate in the reaction. The reaction coordinate does help us imagine the surface, but the highest point along the reaction coordinate is the saddle. At the point, the potential energy is the highest along the reaction coordinate, but it is the lowest in direction perpendicular to the reaction coordinate. The reaction system at this point is said to be the transition state. D is a high plateau giving the potential energy of three atoms well detached from one another. As A approaches a non-vibrating BC molecule, the point represents the configuration of the system that moves along the minimum energy path, that is, the dashed line in figure. The kinetic energy gets converted into potential energy as RAB is decreased. The point indicating the system of three nuclei moves up the valley from the left. If the system of three nuclei has sufficient kinetic energy, they moves up the valley from the left or go over the saddle point. When AB and C are created and acquire energy as the system goes down the valley to the right. The system gets back down the valley to the left if the kinetic energy is less. This is articulated by telling that the reactants recoil each other. Figure is applicable only when the nuclei are forced to align if angle theta is changed. The potential energy surface will be changed. It is very hard to find out quantum mechanically a precise potential energy surface for reaction of type 1. Surfaces have been calculated only for a few reactions. The reaction of a hydrogen atom with a hydrogen molecule has been broadly studied. Counter diagrams shows the potential energy surface for this reaction at theta is equals to 180 degree. This surface has been found out by M. Karplus and R. N. Porter with the help of ab initio methods with configuration interaction. The error at any point on the surface is less than 0.03 electron volt. As hydrogen atom A approaches hydrogen molecule HbHc along the minimum energy path, the potential energy of the system increases until the saddle point is reached. At this point, RAB is equals to RBC is equals to 93 picometer and the potential energy of the system is 0.37 electron volt. The highest point along the dashed line, since the saddle point is 0.37 electron volt, higher than the potential of HA and HbHc at an infinite distance, this energy must be provided from relative kinetic energy or vibration energy in order for the reaction to take place. In the upper right hand corner, a high plateau with energy of 432 kilojoules per mole is situated. This is the energy of three hydrogen atoms substantially far apart with respect to separated reactants or products. Now let us summarize. Macroscopic kinetics is a part of molecular reaction dynamics. The molecular beam process is an experimental technique of studying molecular reaction dynamics in which monoenergetic beam of electrons or molecules are examined by reaction dynamics. Supersonic nozzle sources generate beam intensities larger by 3 orders of magnitude, which helps removing drawback of modern molecular beam experiment. From the simplest reaction, 3 coordinates that are required are the internuclear distance R1 between H and H, the distance R2 of D from the midpoint of the HH bond, third, the angle theta between the HH bond and the vector from the midpoint of the bond to D. And the last, the plot of chemical reaction from beginning to end are provided by potential energy surfaces.